All right, good morning. My name is Nader. I'm assistant professor of software engineering at Robert Morris University. So today, I'll talk about how to better test embedded system, a system that is controlled by software. So the agenda for today, we have a problem statement. I'll talk about the problem we are trying to solve. What is the motivation? I'll give you some background and raise research questions. The method that we use to solve the problem. Then in number 4, we'll talk about testing, the new testing methodology. So the new testing process. And this testing methodology is broken down into 3 sections. Then I will move to major findings and contribution to this work, application and the significance of the findings. And I will conclude with future work. All right, so the problem we have in testing is very costly, right? And testing is a most important activity to validate software system. And the system becomes very complex, and that will increase the cost of testing. Basically, the important part of testing is to generate test cases. So test case is basically the one to stimulate a software or system, and that will give you like a result, probably pass or fail. So generation of test cases is a most intellectually demanding task, and this is where we spend, the cost of testing. If we take a technique, model-driven testing, so this is basically you can derive tests from models. So you need to build a model, a behavioral model. And then from this model, we can derive or generate automatically the test cases. So it has potential, MDT has potential to automate and decrease the cost of testing. One of the challenge that MDT, model-driven testing, is how to transform your behavioral model, very abstract, to platform specific, to a scripting language, to a platform where you can run and test your software. Some background, we have modeling notation, UCM, use case map. So we use this notation to describe a system requirement in very abstract way, very high level of abstraction. Another modeling notation specifically for testing is TDL, test description language. So basically we use it to describe a test as scenario. It is also abstract. We cannot execute TDL on a system. And we have a scripting language. We call this scripting language TTCN3. So this is where you can define a test case. You can put your input test and you run this test case that will generate output. So you just observe the output, the actual output, and you compare it to the expected one just to see if the test case pass or fail. So we have three domain-specific language, UCM, TDL, and TTCN3. And those are the building block of our testing methodology. So our motivation is to develop a testing methodology that enables the automation of or generation of test cases. So we have some research questions. How we can start? What's the starting point of building this testing methodology? So probably we can start with a legacy software test, with something that works already, and we try to migrate it, to TDL, to UCM, to TTCN3, and see if it works. So this is our first research question. The second one, once we build the new testing methodology, how we can execute it, how the model transformation, from behavioral model to test cases is performed. And last question is to validate, to assess the correctness of this new testing methodology. So we need to test if it works, and we evaluate its efficiency. So to tackle this problem, our research method is to start from a large-scale case study, so legacy system. And we will use it to develop and build our testing methodology. To assess the feasibility, we'll take a public case study. So this public case study, we'll just we take the requirements, we describe them in UCM, and then we transform these models to TDL, and then from TDL test scenario to executable test cases. So we run or we execute the testing methodology using this public case study. And to demonstrate the effectiveness of the testing methodology, we will use, we used private case study. So this research was conducted in the avionics industry lab on a device, we call it flight management system. So just briefly, flight management system is a device where pilots can use it to create a flight plan. So they, for example, just say, okay, I want to fly from this airport to that airport, and the system will create a flight plan to follow. All right, so number 4 is our new testing methodology composed of 3 modeling or 3 domain-specific language. UCM to represent system under test requirement. The second domain language is TDL, test description language. So we can represent test specification. And the last one is TTCN3. This is a scripting language. This is where we can run a test case. So our goal is how we can, starting from UCM, where we can, see our test objectives or goals, how we can transform those test goals to less abstract notation, to test specification. And then we take each test specification and we plug in the test input and the test oracle, right, to build or develop test cases. So this is how the approach works. So I'll try to explain briefly each transformation from test goal to test specification and to test implementation. So this is a starting point. We start from a legacy software test. So there is like a testing process in place where software requirements are described in natural language, right? So we can have abstract test case here. And from the abstract test case, engineers develop executable test case in scripting language. Here, the scripting language used was Eclipse and XML. So what we did, we wrote tools to migrate the code from Ant XML to TTCN3. So we did this code migration, right? And then second phase is to abstract the TTCN3 test case to abstract TDL. So we did code to model. This is like reverse engineering, right? So, and we enrich the abstract test case with, test objectives and we did some enhance and check. So once we did that, we can execute the generation of TTC entry from the abstract TDL. Just to bring to your attention, the dashed lines are manual work, whereas the solid lines are automatic. So here, we can compare it later, the legacy testing process with our new testing methodology, and see if we have some gains. Briefly, I will explain code-to-code migration and code-to-model. So we developed tools to translate the code and to output TTC3 modules. So we need data, we need components, we need behavior. We combine all the elements and we get TTC3 test case. This is code-to-code migration from legacy code to TTC3. And phase 2, we abstract the migrated TTC3 code or modules to TDL basic element. So we had to model test data. We did some abstraction. So we found the equivalency, or we wrote the rules, equivalency rules, to transform the TTC3 data to equivalent in TDL. The same for test configuration element and for test description. And those data set, test configuration and test description, are basic element of TDL. We need to enrich the TDL with test objectives from requirement, just to make sure we have everything in place. So now we do have a testing methodology. We discovered the paths between TDL and TTC3 by doing this reverse engineering. So now what we wanted is to execute the new testing methodology. So we start with requirements. We model the requirements into UCM. And we have behavioral models in UCM. And then based on transformation rules, we transform those models to abstract test cases in TDL. And for each TDL, we use the data model for the test input and test output. And we use the rules between TDL and TTC3 to generate test cases. So the approach was basically starting from UCM. So this is like UCM model. And this is a scenario. The red pass is a scenario. It explains requirement. So using a tool, pass traversal. So we run a pass traversal algorithm to export the scenario definition in XML. And then we took this XML, and based on transformation rules between UCM and TDL, we managed to output test configuration and test description elements. Those are essential in TDL test case. So here you can see like some rules between the scenario definition and the TDL test configuration. You can see like some technical details, but we understand that this element in UCM has corresponding element in TDL. And this is to build the test configuration. For test description, another element in TDL. Also, we developed rules to do the transformation. After you generate the TDL description, we need to do some post-processing, especially for alternative behavior. For the data element, as well, we defined rules between UCM. UCM doesn't have data as such. It has responsibility. And we just check the responsibility that may send or receive data or has interaction. And we developed a data model that interaction in UCM or responsibility has equivalency in TDL and in TTC entry as well. So after this transformation, we output 4 elements: test description, configuration, data set, test objectives. Together, they make one TDL. We validated, and it can compile. So now we are ready to move to the second transformation from TDL to TTC entry. So we took the TDL, the resulting TDL from previous step, along with the data model where you can find test input and data oracle. And we did the transformation to executable test case in TTC entry. So this model transformation process output 4 modules, but together they make one test case in TTC entry. So here again, we have transformation rules between TDL and TTC entry. This is for the data. And for the test configuration. So here you can probably, of course, you need to know like some syntax in TDL and TTC entry. But you understand the objective here is to take this element, gate, and transform it, or find the equivalency in TTC entry, which is port. And other elements, are transformed. This is for interaction, receive and send. More rules between those 2 languages. So now the resulting elements from this model transformation are combined in one executable test case: input module, oracle module, configuration, description, right? So we can import all these modules, and we can have one executable TTC entry. So now is to answer the question how we can assess if this new testing methodology is efficient, is correct. So we need to run a case study. So we took this flight management system device, and again, to create a flight plan for pilots. So we used the legacy software test, the process that was already working, but it takes a lot to develop test. It is costly, labor intensive. So we took some requirements, and we want to run them on the new testing methodology. So the assessment was to make sure the legacy and the new testing methodology have same sequence of test and verdict. Like a test case gives pass on the legacy, should give pass on the new testing methodology. So we selected the 3 use cases that reflect largely the FMS functionality. We have some numbers here, like we have like 803 exchange messages, and we have 338 test verdicts. So we did this validation of our model transformation. So for each use case, we applied, we checked if the requirement stage, has a full coverage. If we can generate tests in TDL, and we can run also the test cases, right? And of course, once you run the test cases, we want to compare the result with the legacy. So I have some metrics here, like those three use cases. They are modeled in UCM. So we have like 3 main scenarios for this use case, 9, let's say, unnormal scenario or secondary. So number of test cases in TDL can be 12. So the requirement coverage was 100%. So the TDL covers all the UCM requirement. It is true for the second and third use case. This is the number of input and output exchange for each test scenario in TDL, and the number of verdict, like pass or fail per test case. So we have the total. And now we compared the legacy verdict with the new testing methodology. We scored high in the first 2 test cases, 100%. Very few verdict did not match, but still very promising. So we made sure the testing methodology is efficient and it is correct comparing to the legacy. So our major finding, we reduced test effort. So number of iterations to get correct test cases is reduced. Why? Because we have automation now. Okay, so engineers will not work anymore on developing manually the test case from natural language. You have the model, you push a button, you have the test case. We can start a test early. Okay, so test cases are generated as soon as requirements are captured or changed. Repeated tests are enabled, right? So we can, run the test several times just to make sure it is conclusive, robust. We reduced human errors, right? If you develop manually test case, so potentially we tend to make errors, right? And traceability is another finding. So the execution result, test case pass or fail, can be traced back to the requirement, just to know this requirement, yes, it was tested, or not, is not tested. Automation of the process was one of the major contribution. This automated approach, right? Generating test cases from requirements, elevate the stress on practitioners, on engineers to deliver quality work. Implication and significance of the finding, this approach is using modeling and model transformation. So it can serve as a concrete application for modeling. So it's like we gave like evidence, modeling and model transformation is a good technique and can, enable automation. To conclude, so we developed, validated, and automated flexible model-driven testing approach based on 3 domain-specific language and model transformation for testing embedded system. Future work, probably we can automatically record the links between the transformations. So between UCM here and the TDL, it is possible it's possible to automate the recording, also between TDL and the TTC entry. All right, I think I finished on time.